Super thrilled to have Hirsch join us today to talk about AppWorld. Hirsch is, as most of you know, he's a final year PhD student at Stony Brook, and he has done a lot of work in reasoning, from model building to creating benchmarks to robust evaluation metrics. And today he'll talk about AppWorld, and he has been doing this AppWorld tour for like the last several weeks, talking about AppWorld many places. Exciting piece of work. He was an intern with us. He is also a very active collaborator since then. I think as of yesterday, he has the most gigabytes on our NFS skill system. It's good to have him. He spent a week here with us. He'll be here after the talk today, all of the rest of the day, and all of Monday. So if you'd like to meet him, online or in person, there's a sign-up sheet in the invite, and that'll be great.
All right, cool. Thanks, Ashish, for the introduction, and thank you, everyone, for coming to this presentation. Today, I'm super excited to talk about our work, AppWorld, reliable evaluation of interactive agents in a world of apps and people. This is joint work with many of my amazing collaborators from Stony Brook University, Allen Institute for AI, and Saarland University. So I want to start this talk by painting a broad vision behind this project before diving into the specific work. So many of us have already used AI agents that act on our behalf in the digital world. Assistants like Siri, Alexa, and Google Assistant are agents that can already do simple tasks on our behalf, like setting an alarm, checking weather, and making a call. In the future, I believe these AI agents will become far more capable. They will be used for doing more complex tasks and will be adopted and integrated even more broadly into our society. Everyone will have their own personalized AI agent through which they will interface with the digital world and to some extent, even the physical world. So these agents will coordinate with each other and even with humans to achieve complex collaborative tasks. And there will also be agents that act on behalf of organizations like hospitals, banks, and so on. They will deal with real-world resources, and their actions will have real-world consequences like transferring money, sending medical records, and so on. So as we move towards such a world, it is important to ensure that these agents become more capable, reliable, and trustworthy. Our long-term goal of this project is to build a simulated world which acts as a foundation for reliable evaluation and development of such agents embedded into our society. And AppWorld is a step towards this long-term goal. And that is what I'll talk about next. AppWorld is a simulated world and a benchmark which focuses on a setting where AI agents individually and autonomously complete day-to-day tasks on behalf of people on their app accounts. It includes tasks such as returning an Amazon order and buying a replacement, sending owed money to friends on Venmo, and canceling meeting reminders based on coworkers' emails. Now, agents can operate apps to do such tasks broadly in two ways: by interacting with the browser or mobile user interface, or by calling APIs exposed by these apps. Towards the end of this talk, I'll talk about our ongoing work on agents interacting with the user interface. But for most of this talk, I'll focus on agents calling APIs. Now, although calling APIs is the main ingredient, just that is not enough for complex tasks. For complex tasks, calls to these APIs also have to be made by writing rich code in an interactive manner. Let me explain it by showing how an ideal agent can tackle an example task, which is play my shortest Spotify playlist with enough songs for today's workout. My workout plan is in simple note. To solve this task, the agent first has to find the user's today's workout duration. To do this, the agent obtains the user's simple note credentials, logs in, and searches for the workout related notes. And it does all of this by writing a code snippet, making appropriate API calls to the simple node app. Now, notice here that the output of the first API is going as an input to the second API. Still, both API calls can be made into the same code snippet. And this is possible if the agent knows the output schema or type information of the first API and input schema or type information of the second API. However, what to do next depends on the free-form text present in the nodes variable. So the agent has to print it. The agent sees a node with free-form text indicating day-wise workout durations. And so it prints the current day to find today's duration. Now, notice here that the agent printed the current day because it found a node with day-wise workouts. However, users' nodes could have been organized in many number of ways, and each of those ways would have required a different code snippet. For example, if the agent saw a node with month-wise workouts, it would have printed the current month instead. So this means that here the second code snippet had to be written interactively based on the first code snippet's output. All right, so now the agent knows that it is 45 minutes. Today is Tuesday, so it is 45 minutes. And then it searches for the user's shortest playlist with enough songs for this duration. And to do this, it has to loop over the playlist, find their individual durations, and then filter and select them accordingly. Doing this involves writing rich code with various programming constructs like loops, conditionals, arithmetic, and so on. So in summary, we saw that a seemingly simple day-to-day task can be quite complex, and it had two key requirements. It required environment interaction to write the next code snippet, and the code itself was rich with various programming constructs. So the key question we ask in this work is that how can we develop and benchmark such rich and interactive coding agents for complex digital tasks in a rigorous and reproducible manner? To do this, we need three ingredients, as it will become clear later. We need a rich and reproducible environment of API operable apps for agents to interact with. We need a benchmark of complex tasks requiring API calls with rich and interactive coding. And we need a robust and programmatic evaluation framework for checking agents' code completion. Now, there have been many tool use or API use benchmarks like Gorilla, Toolbench, API Bank, and many more. However, they do not support these requirements. Their tasks are simple with only a linear sequence of 1 to 4 API calls. They have small number of API implementations or use unstable APIs. And they use human or LLM judgment or reference-based evaluation, which is not robust for complex tasks that can be solved in many ways. So to bridge this gap, we introduce AppWorld, which constitutes a new environment, a challenging benchmark, and a robust evaluation framework. And I'll talk about these three components, starting with the environment. All right, so we want to create an environment of API operable apps like Amazon, Gmail, Venmo, and so on. We also want this environment to support reproducible experiments, complex tasks, and robust evaluation. Reproducible experiments require resetting the start environment to identical state whenever we want to run an agent on a task. Complex tasks require tailoring the start environment specifically for the task to be compatible and challenging. And robust evaluation requires accessing the final environment state, as complex tasks can be solved in many ways. So this means that we need full control on the state of the environment, which for an app-based environment is defined by the databases underlying these apps. So this means that we need full control on the app databases. Now, this rules out the option to build this environment from real apps implemented by companies because their app databases are fully controllable only by them and not by us. So instead, we implement simulated versions of these apps in our own backend of APIs and databases. This provides us with full control. This provides us or anyone else with full control over the app databases. Simulated apps also have other advantages over real apps. For example, real apps would require real money, like a Venmo payment. Real apps would require real resources. For example, a Venmo payment requires real money. Whereas in our simulated app, payment would be just a database entry indicating who paid whom what. Simulated apps also are fast, always available, and have no rate limits, which is not the case for real apps. But all of these benefits of simulated apps are not enough. We also need richness, realism, and complexity of real apps. And for this, we have spent huge amount of effort in this work in making this simulated apps to be super rich and high fidelity in nature. This means that they have closely similar features and behavior to real apps. Our app implementations span over 60,000 lines of code, have 457 APIs with very detailed API documentation and 100+ database tables. These apps have fine-grained and detailed functionalities. For example, the Gmail app won't be just send and read emails. As it is in real life, emails will be organized in threads within your inbox and outbox. You can reply to and forward individual emails from them to different contacts. You can schedule them for a future time. You can manage your drafts, attachments, labels, do search over them, and a whole bunch of other things. Actions or API calls in these apps also lead to realistic in-app and cross-app consequences. For example, when you place an Amazon order, your cart is cleared, the Amazon product inventory is updated, the order shows up in your past orders with the tracking information, and you also get an email confirmation with a receipt as an attachment. These apps also have authentication and privacy features like login, sign up, forget and reset passwords, and prevent access to others' private information as well. And these APIs also always provide informative error messages. For example, if the agent attempts to send money to someone via a payment card that does not have enough balance, the API will respond with a message saying so. And this will help the agent to learn via interaction. These apps have also been extremely rigorously unit tested. We have over 1,700+ unit tests spanning over 34,000 lines of code and providing a test code coverage of 98%. We wanted it to be such that agents can explore and operate this environment arbitrarily without the environment breaking or behaving unexpectedly. And this rigorous testing gives us high degree of confidence that we have such a reliable environment. And as mentioned before, these apps also provide full programmatic control over the database state. And we use this control to populate app databases with rich and realistic data. And as I will explain later, this data will help us build complex tasks. All right, so we create a simulated world of 100+ people. In this world, each person has personal accounts on all apps. They also have a home and work address for online delivery and payment cards for monetary transactions. And this allows us to have personal tasks like buy a t-shirt for my home delivery using my Visa card. People in this world are also related via various relationships like parent, friend, sibling, partner, and so on. And this allows us to have relational tasks like email my partner that I'm running late. These apps are also populated with realistic personal and interpersonal digital activities of people which are consistent with their relationships. For example, on the top, you see an employee sending an email to his manager asking for a leave approval. And on the left, you see two roommates chatting about apartment bill payment over phone messages, and so on. And these activities are populated spanning 2+ years of time, which allows for temporal tasks like delete my emails from last year. Overall, the resulting database has 100+ tables, 350K+ rows, and 750+ columns. Now, I don't have much time to go in detail, but just note that this data is generated procedurally by sampling from human-in-the-loop LLM-generated data, as opposed to via people simulated via LLM agents. The resulting world of apps and people, which we call base world, provides us with a rich and realistic foundation to build the complex tasks on top of. And I will show how we use it to build complex tasks later in the benchmark section. So next I'll talk about the benchmark, but I can also take a few questions.
I have a question about the criteria that you showed when you're like building the simulated apps. I guess I'm assuming you want it to be as faithful as possible to like what we know these apps actually have, like in their,
Exactly.
I guess, UIs. But in terms of the expressive errors, how is that something you actually know? You don't know like the API errors, right? That's a design choice that you made.
Yeah, so we try to be as informative in error messages as possible. Yeah, that's pretty much it. Basically, the way we implemented and designed all of these apps, we just made like a catalog of all the features present in these apps, and then figured out how we implement them. And in implementing them, you also need to make design decisions on how to design APIs, which APIs should be there, what should be the responses, and so on. And in following that, in doing that, we follow this kind of REST principles and try to follow as many standard conventions as possible. And for some apps, the API documentation are also available online, so you could also refer to that as kind of a reference to guide your designing process. That's a great question, though. Yeah.
Maybe you just answered it, but is the documentation for the APIs extensive, or?
It is very extensive. You have a documentation of what API is, how it behaves. You have documentation on all the arguments, constraints on them, type information, one-line description of them. And we also have this very detailed response schemas as well as what the JSON or JSON schema of the response would look like with type information and everything.
The reason I'm asking, and maybe you'll get to this, is that of course those are the resources that an autonomous agent would be using.
Exactly. Yeah. Yeah.
Maybe a quick question about the interaction that you described here. It's mostly agent and environment, right? We don't have any user interaction at this point. I said that the example you had in the paper was play my Spotify playlist, but the example here is play my shortest playlist, which I thought, you want to remove the ambiguity, which you could resolve if you have user agent interaction.
I think that choice was not based on anything like that. It was only because if the shortest word is kind of removed, then you can always pick like the longest playlist. There is a small shortcut there.
Okay.
So I kind of simplified that example for presentation purposes in the paper and here also, but then someone pointed this out to me and then I said, okay, I should put it back. But your point is very valid. Currently there is only agent environment interaction, but sometimes you want human to also be involved. Maybe the task instruction is not clear enough. Maybe agent should come back with clarification question, or maybe there should be some follow-up there. Sometimes humans also give wrong instruction. Maybe they just forgot about something. So maybe if the agent finds something like that, maybe it should come back and ask for more clarification questions and things like that. So there is an extension of this work, which is very much possible, where you would just have a simulated user via a GPT, and you could give our instruction to that user, and there would be a 3-way conversation. So it is an extension we are thinking of, and we might have that in the future, but that's not the setting in this work. One of the key reasons of doing that was that we wanted the evaluation to be very concrete and objective, If you add the simulated user, which is mocked by GPT, then there is this additional, kind of murkiness, like where is the error coming from? Is it from the user, simulated user, or it's coming from agent? So, thanks. All right, so next I'll talk about the how we build the benchmark and specifically how we design complex tasks. So we start by writing this day-to-day scenarios that naturally require rich and interactive reasoning. Here, a scenario is an ungrounded blueprint for the task. For example, buy the product that my related person suggested someday. Using this scenario, one can create multiple tasks, like buy the shirt that my roommate suggested today, buy the desk my coworker suggested yesterday, and so on. However, note that we want the agent to follow the instruction in the environment by taking actions. So just instruction is not enough to define a task. We also need a world state, which is the database state and current time within the world, and the supervisor, who is the person in the world on whose behalf the agent is supposed to operate apps. Now, for these tasks to be solvable, we need to ensure that the instruction, world state, and the supervisor are compatible with each other. This means that all conditions required to follow the instruction are satisfied in the world state for the supervisor. For example, in this task, the current time is 11th of February, and the supervisor is Alice. And as per the database, Alice's roommate has suggested her to buy a Nike shirt today via a phone conversation that you can see over here. This Nike shirt is available now in Amazon, and Alice, at least one of the payment cards of Alice, has enough funds to make the purchase. Now, these conditions make the task solvable. But mere solvability is not enough. We also want the task to require thorough reasoning to solve. And for this, we include distractors, hurdles, and task variations. Here, including distractors means that making it so that bypassing any reasoning step will likely mislead the agent to the wrong path. For example, here Alice would not only have suggestions from today, but also from days before. So if the agent ignores the word today, it will likely fail to identify the correct shirt to order. And similarly, there will be other distractors as well. So if the agent ignores the word shirt or roommate, it will similarly also get distracted. We also include task hurdles, which requires agents to do realistic failure handling and adaptation. For example, here, one of the payment cards of Alice has no money in it. So agent has to realize to try another card when that one fails. And we also include task variations, which require agents to reliably solve tasks under slightly different contrastive conditions. For example, remember that we created this task by grounding a scenario. Similarly, we can create a different task by differently grounding the same scenario. Notice here that the two tasks have different current time and supervisor. They have different placeholder values, and they have different database states. Note that these task variations are carefully designed to also catch shortcuts that distractors cannot. For example, in this case, on the left, the key relevant suggestion has come via a phone message, and on the right, it has come via an email. So therefore, agent needs to check both phone and email for suggestions to succeed on both the tasks. All right, so now that we know what we want from the tasks, let's see how to ground the scenario to satisfy the required initial conditions. To do this, we use the base world that we discussed earlier. Remember that the base world already has a rich, fully populated app databases, including people and their app activities. This base world provides a reusable foundation that can be used across all scenarios, but it does not satisfy task-specific requirements. So we will need to adapt it for each task, as I will show in a bit. So to ground the scenario, we need to do two things. We need to select the placeholder values like shirt for a product, roommate for the related person, and so on. And we also need to satisfy the required initial conditions as well. Now, some of these conditions can be satisfied by doing a search over the app databases in the base world. For example, to find a compatible supervisor, we can just find a person in the world who has roommates. However, other conditions cannot be satisfied by search alone. For them, we need to edit the app databases. For example, the base world would not have a specific phone conversation about shirt suggestion between Alice and her roommate. So we need to create one, which will require editing the database. Now note that this is kind of a very simplified picture. In practice, there are many conditions, often interdependent with each others. So for the flexibility, we do all of this programmatically by writing the task setup code for each and every scenario. All right, so now we know, now that we have created the task, we want to programmatically guarantee that these tasks are indeed solvable. And to do this, we write the solution code and evaluation tests for each task, and then we programmatically verify that running the solution code passes all evaluation tests for all tasks. Now, here I want to emphasize that each scenario has unique requirements. So all code has to be written individually for every task scenario, which has taken over 5 hours of time for every scenario and over 40,000 lines of code. And to ensure high quality, all scenarios and code have been developed by us. It is not crowdsourced, and it has been reviewed multiple times by multiple people. And here are some example tasks. I'll go over the first 2 of them. The first one is I'm going on a camping trip with my siblings. I emailed them a checklist of the needed items, check who committed to bring what, then order the remaining items on Amazon. And the second is I booked a few hotel rooms today for my upcoming trip. How much did I spend in total from my Visa card based on the email confirmations? And so on. All right, so to solve these tasks, the agent is given the instruction, API documentation to understand how to use the APIs, and an interactive coding shell with an API client to call APIs. Using this shell, agent can, for example, log into Spotify, explore API documentation interactively, and can obtain personal information about the supervisor. By default, to do this, we provide an IPython-based shell, but one can really use any programming language or HTTP client of their choice. So based on our written solutions, we find that these tasks are quite challenging. They have 1 to 4 apps. They require 1 to 4 apps, 5 to 25 unique APIs, 10 to 200 API calls, and 20 to 130 lines of code. We have overall 750 such tasks built from 250 scenarios. Remember that each task scenario can have multiple apps. From across all of the 9 available apps, we hold out 2 apps, Amazon and Gmail. And all the tasks involving any of these 2 held out apps are moved into this test challenge split. And the remaining are randomly divided in train, dev, and test normal splits. Notice here that we have 2 test sets, test normal and test challenge. Of these, the test challenge is our main test set, as it forces learning to use APIs for held out apps by reading and understanding the documentation. And it also turns out that test challenge has inherently harder tasks. All right, so next I'll talk about evaluation, but I can take a few questions here again.
I have a quick question. It seems like an incredibly high fidelity environment. Are there any aspects of the real world that you have not modeled that are significant?
Yeah, so basic assumption here was that everything that we have like all the apps and consequences that we have in the things that we have implemented would behave correctly. For example, if you place an Amazon order, you would get an email confirmation, right? And then you can use that email confirmation. Maybe if you have an attachment, you can download the file and you can maybe zip it with some other file, send it to someone. All of this is doable, and we make sure it happens because all of these kind of constructs or things are existing in our environment. We have an email app, we have a file system app, and we have an Amazon app. But the aspect of the real world, which is kind of not captured, is that I mean, of course, you wouldn't kind of like literally get like a package on your doorstep. That is kind of the obvious thing. But also things like if the package, yeah, basically things that we have in the environment would be satisfied, but things that we have not modeled, there will be just no way of capturing that.
I was wondering if there's, the real world can be quite messy. It can be, we have sometimes the documentation is bad or missing. Sometimes apps fail. Sometimes error messages are completely uninformative. Sometimes apps can be maybe there's some.
I see.
Maybe the real world is. Maybe AppWorld is an idealized version of the real world in some sense.
Got it. So I kind of misinterpreted what you meant by real world. Yeah, so I completely agree. So I think there are many cases where in like real world, first, like maybe documentation is not available, or maybe if documentation is available, it is kind of noisy. So all of these things are in fact true. And one thing that you could do as kind of an extension of it is that you start with this AppWorld environment, and then you kind of try to inject real world kind of noise to it. So maybe kind of drop some APIs, or maybe make some of the documentation noisy, things like that. So currently our focus is that let's just make sure everything is solvable, and that is our focus. And we will evaluate the agents on that kind of objective level. Now it is kind of a separate question that if the APIs are not well documented, or they are unavailable, like how can the agents operate? And I think there could be like extensions of AppWorld where this question could be answered. Does that answer your question?
Yeah, thanks a lot.
Thanks.
Yeah, my question was pretty similar. Like, I just imagine when I use Siri or something, it's like, oh, text mom, I'm running late. It's like, who's mom? It's like, okay,
Yeah.
in the app world, that might not be an entry from me to mom, but everybody's got mom. So clearly, like, it's just like a kind of
Got it. So I think
messiness of the real world, right?
Yeah. So in this case, let me just clarify how agent would resolve it is that we have this kind of a phone app, and in the phone app there's a contact book, and in the contact book there are like different contacts, and there would be a field for relationship where it would be mentioned, and the agent wouldn't know it a priori, but would have to explore, okay, what apps are available within apps, what are the APIs which are available, and then would find out there's this contact book, maybe here's what I can look into.
That still seems pretty faithful to the real world.
Yeah.
Like the agent, I guess, still is LLM. It still has to figure out the language to the structured translation.
Yeah. So nowhere in the instruction would say that mom's number is this. It would basically have to find it out.
Right. I guess what I'm saying is like in my personal phone's database, maybe there's not like explicitly set that you go like mom, this contact.
Yeah. Here is another thing we can also do. We can also kind of remove those entries because the world that we have, like the data that we have created, in those there would be conversation of the user with his or her or her mom, and that conversation would also be kind of the conversation that one would have with their mother, right? So there is a way of inference there as well, but we didn't want to kind of make it kind of murky, right? We wanted it to be like objectively solvable, so that's why we chose this. But you could extend this for other reasons.
There was a hand earlier.
Hi, I raised the hand.
Yeah.
Hi, Harsh, Bhavna here. So, very exciting talk. I just had a question about the distractors that you mentioned earlier.
Yeah.
So, I understand that you will be evaluating whether the task was solved as expected. which would be the gold solution and its unit test. Maybe you will cover this later, but is there also an opportunity to understand where are the agents getting distracted or fooled by in your environment?
Yeah, so I think one would currently at least have to do that manual error analysis to figure that out, because the tasks are like quite. I mean, it would require it could require like hundreds of lines of code, like many interactions, and there is no kind of automatic structured way of kind of doing that systematic analysis on where exactly it failed. And this kind of even is kind of difficult because sometimes there are like many ways of doing it. So there is no automatic way, but one could kind of look into the trajectories and answer that.
Thank you.
Cool.
Clarification
Yeah.
on the train test split. So you mentioned about the test split having things like the Amazon and Gmail.
Yeah.
using those two. So does it mean that any activity that triggers those two or will be like not in the test? Will be not in train.
So the train would not have Amazon and Gmail. Everything else it would have.
Maybe like one of those apps could trigger, say, an email message, and those will also not be in the train. Like, what if a triggering thing?
Triggering. Okay, so the way we determine this is that we write the solution, and in the solution, if there is I have triggered an email app, then it would be constituted as a usage. But if I've placed an Amazon order and the Amazon app itself triggered an email message, we wouldn't consider that a usage. Does that make sense?
Yeah, it makes sense. Thank you.
Okay, I think I should move on. Okay, so next I want to talk about the evaluation, and specifically, how can we robustly and programmatically evaluate agents? Now, there are many ways of completing these complex tasks can be completed in many ways. For example, if the agent wants to, let's say, download an Amazon receipt for an order, it can download it from its corresponding API, or it can download it from the email confirmation that was sent to it for the order. And both are like completely valid approaches. So comparison to a reference solution is not suitable in this case. And that's why we use state and execution based approach. In particular, the agent starts with the initial database state of the world. It does this series of code executions, and then we get kind of a final database state. We then compute a database difference between the initial and the final database state to obtain the cumulative changes that the agent has made to the tables, rows, and columns. And then we programmatically check whether they include all desired and no undesired changes. And we do this check hierarchically, going from tables to rows to columns. For example, for our Amazon task about buying a t-shirt, we would first check that only a small list of tables have changed, like Amazon orders, inventory, and so on. And this very simple check captures vastly many ways agent could have made undesired changes or collateral damage. For example, if the agent was asked to buy something and it ended up returning something, then the Amazon returns table would change and this test would fail. And then we check that only one row has been added to the Amazon orders, and that row corresponds to the Nike shirt that was supposed to be bought. So the key effect of doing all of this is that regardless of what path the agent chooses in making the desired changes, it will pass. And regardless of what way the agent makes an undesired change, it will fail. And using this tests, we define two evaluation metrics: task goal completion, which checks that all tests in a task pass, and scenario goal completion, which checks that all tests for all three scenarios in a task pass. All right, so next I'll talk about the experiments. So we benchmark agents built from open and closed LLMs by carefully adapting 4 strong few-shot prompting methods. The first one is React, which I'll talk in a bit. The others include plan and execute, which acts a planning stage before React. The function calling, which leverages native parallel function calling ability of language models, and full code plus reflection, which attempts to generate full code for the task in one go, and then retries by reflecting on the error stack trace. In interest of time, I will only explain the first prompting method, which is React. First prompting method, which also turns out to be the strongest. All right, so React first generates a natural language thought about what it wants to do, and then follows it up with a code snippet to do that. Depending on whether the code executed appropriately or not, the environment returns an output or an error stack trace, based on which the agent decides what to do next, and this sequence continues. All right, so next, let's see the results. On the x-axis, you see different open and closed LLMs. On the y-axis, you see the task goal completion of the test on the test normal split. And the score here, which I will show in a bit, refer to the maximum score achieved by an LLM across all 4 few-shot prompting methods. So as you can see, the best performing model, which is GPT-4o, still struggles getting only under 50 points, and all other models are much behind it. And it turns out that this is in fact the easiest setting. Next, I'll talk about the robustness of the agents. Remember that the scenario goal completion captures whether agent could complete all 3 tasks of a scenario correctly, and these tasks from a same scenario are variations of each other's. And when we go from the task goal completion to scenario goal completion, we see that all scores significantly drop further. For example, GPT-4o drops by 17 points, going from 49 to 32 points. And when we look at when we go from the test normal to test challenge split, which is our main test set, all scores significantly drop further. For example, GPT-4o obtains only 13 points in the scenario goal completion. And when we break down the GPT-4o numbers into individual prompting methods, we see that GPT-4o performs best with React in both the task goal completion and scenario goal completion metrics. We have graded Apple tasks in 3 levels of difficulty, which allows us to assess how agents are behaving and performing at different levels of difficulty. The histogram here shows the distribution of tasks as per the difficulty levels, and the lines show the task goal completion score of different prompting methods. And as you can see, going from level 1 to level 3, the best performing method drops from close to 55 to close to 20, and this shows that agents struggle quite a bit more on harder subsets of AppWorld. And we also see similar trend in other indicators of difficulty, like number of APIs and number of lines of code as per our written solutions. And finally, based on some manual error analysis, they find that agents make variety of mistakes. For example, they make incorrect assumptions about the environment without looking into or interacting with the environment. For example, here in the Amazon task, the agent assumes that the suggestion has come via a phone message and doesn't check emails. And as a result, it fails. Agents also struggle to adapt based on errors properly. For example, on placing the Amazon order, when the environment says the payment card doesn't have enough balance, the agent gives up instead of trying another card. And agents also forget state because of a long trajectory. For example, React trajectories are often more than 35 steps. And they use APIs incorrectly, ignore crucial pieces of instruction, and make variety of coding and common sense errors. All right, so I can take a few questions here before, maybe I can take a couple of questions.
how are you providing, is this, like, when you give all the API documentation, are you just giving it all in context, or is it a retrieval-based thing, or the agent's like, oh, I want the API docs for these 3 apps, or how does that
Yeah,
work?
excellent question. So there are 2 ways we do it. The first way is kind of we have this API Explorer app, which has APIs for exploring the API documentation itself. For example, it would have APIs to say, okay, what are the apps which are available within apps? Give me like 1-line descriptions of all the APIs. And once I've decided everything, give me then the full API documentation of that API. So 2 of our methods, which are kind of more agentic, like React and plan and execute, for them, we use this approach. And there is a second approach, which is kind of like just API retriever, where we just ask an LLM with all 1-line descriptions of all APIs and tell it, given this instruction, what APIs are available, what APIs should be used. So it's a direct approach. And so we use both of them depending on the prompting method. Yeah.
It's not entirely obvious to me that this database difference strategy is going to capture every, that it's going to not lead to problems of the kind that you motivate in the first place. So is it true that every scenario has a unique database trace that should always be true?
No, that is not. That's fine. You can still write. So I'll just give you one quick example. Let's say the task, we don't have a simple task, but let's say the task is buy me a shirt. If the agent ends up buying a red shirt, blue shirt, green shirt, Nike shirt, whatever, they would all lead to different database states. And there are different paths to go to different database states. However, you can still do the difference, and then you can write a programmatic test that the row that changed in Amazon orders is a t-shirt. That's all one needs to check.
Mm-hmm.
Does that make sense?
Yeah. But do you have some guarantee that that's always going to be possible with the scenarios that you have?
So all of this is just done manually, and we just do that. Yeah. And the reason we do the difference is that captures everything the agent could have done. And then we account for everything in that difference test. So if the agent, if you asked it to buy something, ended up like, let's say, starting like a Prime subscription, it will show up in the difference. So then you can say, oh, this is not what we asked for. Yeah, so we can give it like a bad score. All right, so next I want to talk about some ongoing and future work. All right, so as we have already seen, Apple requires many skills to solve tasks, like writing code as per documentation, interacting with the environment, dealing with long-range dependencies, and so on. Apple provides a rich and flexible development environment for exploring research methods for learning these skills. These skills are also applicable to solving other complex tasks in other domains, for example, science and software engineering, but they are harder to acquire in the available environments. And to acquire these skills and make progress on Apple, there are many research directions one can pursue, like learning to self-play on top of Apple environment, curating a training data for interactive coding with API calls, learning a higher level skill or function library, and exploring planning-based, search-based, and memory-augmented approaches. And soon all of this research will also be doable in multimodal version of AppWorld. So far, we have talked about agents calling APIs, but sometimes apps do not expose APIs. So agents should also be able to interact with the browser and mobile user interface directly to solve these tasks. In this work, we implemented many apps, API operable apps in our own local backend of APIs and databases, which can be operated via an API or HTTP client. In the follow-up work, we have also developed browser and mobile user interfaces for all apps. The UI is closely similar to real apps, and it is backed by the same backend of APIs and databases. So this means that agents can now operate over all modalities to solve Apple tasks. And because Apple tasks and evaluations are database state-based and process agnostic, all the work that we put in developing this complex tasks can be reused as is. All right, so finally, I want to take a step back from what we've proposed in this work and revisit the broad vision that we started with to lay out some more future work. So we envision this future where AI agents will get deeply embedded into our society and will take various roles and responsibilities. In such a society, agents will have to collaborate with other agents and even with humans to achieve complex tasks. They will have to work in messy real-world environment, which requires dealing with failures. They will have to be resourceful, making sure they are not wasting your time, money, and other resources. And because real-world resources are at play, they will also have to be robust to inevitable security attacks. And because, after all, they will deal with people, they will have to be socially intelligent and follow our social norms and expectations. AppWorld provides a fully programmatically controllable society of people with their digital activities. And this foundation can be used for developing and evaluating agents in all of these directions. And if you're interested in any of these, please reach out and I'll be happy to chat further. All right, so in conclusion, we introduced AppWorld, which was born out of a significant engineering effort by our team, writing over 100,000 lines of code. We have developed a rich and fully controllable app environment with simulated activities of people. On top of it, we developed a benchmark of complex tasks with robust programmatic evaluation framework, ensure that best LLMs struggle on it. And we talked about various future works for making better agents and for creating new agent benchmarks. So please check out appworld.dev for task and API Explorer, leaderboard, agent trajectories, playground, and a lot more. We have made AppWorld to be really easy to use, so you can just pip install it and start building and testing your agents. And if you have an agent, the code on the left this is all you need to run and evaluate it on AppWorld. And that's all I have. Thank you. Happy to take questions.
In your experiments, to what extent did you use the training set? Was there like few shot examples, or were there any kind of training?
Yeah, that's a great question. So let me go back. Yeah, so basically the question is, all the experiments that I showed were kind of few shot. So why then we have the training set? And the reason we have it is that first to kind of have some standardization, like some of the previous works had only had like test sets and people take like future demonstrations from them and sometimes even do hyperparameter tuning on them. So like train, dev, and test was partly for that. And if you have the train set, the key property that you get over here in the way we have done things is that regardless of what demonstrations you use over here, the two held out apps would always stay held out. So we have chosen like few demonstrations, but one can really use any of them, and this property would hold. Now, the experiments that I talked about today were only few short demonstrations which we selected. But in the paper, we also have this k nearest neighbor thing, where you select, given the test set, you find the closest nearing demonstration, and that search was done over the train set. In future, people can also use it for like augmenting the training data set in some automated fashion, things like that. Yeah.
Peter had a question.
Yeah.
But I might have missed this. Does an agent get penalized for taking an overly long trajectory to solve the task? And I guess related to that, do you include any impossible tasks, like buy something, but you don't have enough money to buy it, and so there's no way of solving it?
Yeah, that's both excellent questions. So, no, for answer to the first question is no, we don't penalize model. Agent can take as long trajectories as it wants. It turns out that we had this experiment, which I did not show, is that if you look at the score the agent gets at different thresholds of interaction, we see that the scores do improve up to like 35 interactions. But if you see, the trajectories are in fact like going up to 70. So there are like many trajectories for which it's like overly long, nothing is happening. So yeah, so that definitely does happen. We do not penalize it. Agent can basically take whatever long route it can take. But in the future, one can consider, this kind of cost versus efficiency kind of create kind of a Pareto curve and kind of optimize on that. That's definitely something some people are working on. And what was the second question? Can you remind me?
Yeah, do you have any impossible tasks in the benchmark where the agent just cannot achieve it?
Yeah. So again, excellent.
The task is to realize that it can't do the task and give up.
Yeah. So that's again an excellent question. We do not have it in this work because we kind of wanted to take a first step where everything is solvable, objective. But there is a very simple extension of this possible for just this kind of undoable task, make the task undoable, and then have the agent explicitly say that it is undoable. So we are thinking of like extensions of AppWorld where these kinds of tasks would be there. And for us, creating it is actually not very hard. So for example, in this case, the 3 conditions I talked about, let's say if I just make the payment, the balance of all the payment cards to be 0, the task would become unsolvable, right? So it's just like a very small change we can do in the task setup, and it would become unsolvable. And then you kind of get this pair of tasks. One is solvable, one is not solvable, but there is very small difference between them. So it's contrastive by just kind of construction. So we are thinking of like extensions of AppWorld where those new additional undoable tasks would also be there. But that's a great question.
Thanks.
I guess we are at time. Thanks, Harsh.